All right, sorry about that. My mic was muted in the software. So if you're wondering at this moment in time if the whole video is going to be silent and me going blah 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 blah, we're good now. I hope. Now I'm paranoid. Let me just check to make sure that I have audio. Yep. Okay. Okay. Good. Okay. Sorry. So we have audio. We're good. All's good. Right. Totally. Oops. All right. Okay. So you want to know, your question is about what numbers you divide for the calculation of the mass percent of the aliquots. Okay, so let's talk mass percent. So mass percent is a concentration unit. Open actually. Let me. This is a Chem 400 question, and this is for eLab 1. All right, now percent mass is a concentration unit, and percent mass is equal to the mass of the solute divided by the mass of the entire solution times 100. Now, in this instance, our solute is sodium chloride, and our mass, of our solution right here, this is the grams of the aliquot. Right, and I guess just to be a little more explicit, our mass, this will be grams of sodium chloride. So so we can rewrite our expression for mass percent as, actually, let's get this down just a hair. It's going to be the grams of sodium chloride over the grams of the aliquot. All right, times 100. That'll be how you calculate your mass percent. Now, one thing to be aware of is right here. In your numerator, this right here, this is the mass. The mass of sodium chloride in 1 aliquot. All right. In other words, right, so this is the mass of sodium chloride in 1 aliquot. That's another way of saying that this right here is 1/5 of the total mass of sodium chloride. All right, because you weigh out a total mass, that mass was used to make 100 milliliters of the solution, and then, each aliquot is 20 milliliters. So the amount of sodium chloride in 1 aliquot is 1/5 of your total mass. So That's an easy mistake to make. Watch out for that one when you're doing the calculation. Let me know if that clears things up, if that answers your question about the lab. Okay, yeah. Let's see. So you think you did the calculation for the mass, and the thing is, you need you need that calculation. Ah, yes, exactly. You totally got it. Awesome. Victoria, you are so totally welcome. Thank you so much for dropping by and making office hours more interesting, at least for me. It's much better than sitting here all alone. Ashley, fire away. Okay. So let's take a look. Okay. Wait. Why did I? We're still doing Chem 400. But this is an empirical formula. All right, so let's take a look. So we have 75.69% carbon, 15.5, whoa, that's a funky looking 5, 15.51% oxygen, and 8.80% hydrogen by mass. And we're given the molecular weight is 206.29 AMU. And now we're asked to identify the empirical formula and the molecular formula. All right, so we want the empirical formula and the molecular formula. And we have to take this in step. In order to find the molecular formula, you first need the empirical formula. So we're going to begin with the calculation for empirical formula. Now, whenever you're given your percentages of each element in the compound, what you want to do is you want to assume that you have 100 grams. Because if you have 100 grams and 75.69% of that mass is carbon, that means you'll have 75.69 grams of carbon itself. The same goes for oxygen and for hydrogen. All right, now we know with both empirical formula and molecular formula, that the ratio of the subscripts within the formula, those are not mass ratios, those are molar ratios. So to find what those ratios are in the empirical formula, we need to convert each quantity in grams to moles, and we do so using the atomic mass of each element. And these we get from the periodic table. All right, and you can see that all of our mass units will cancel. We'll be left with moles, which is good. And now we need to bust out our calculators and do some number crunching. So let's see, 75.69 divided by 12.01. Sorry, 75.69 divided by, I think it clicked multiply. There we go. It's like that number looks way too big. Now, this is one, sorry, that's 6.3. Zero 2 moles of carbon. 15.51 divided by 16 is 0.9694 moles of oxygen. 8.8 divided by 1.008 is 8 0.730 moles of hydrogen. You'll notice that I'm not really doing rules for sig figs right here, and that's because our final answers are going to be integer numbers. So you don't really have to worry about sig figs. The only thing that can mess you up in a problem like this is rounding too much. So I keep about 5 sig figs or 4 sig figs in there, and that'll be fine. But it's one of the nice things with the empirical formula problems is you kind of get to take a sig fig break. All right, now we know what to do with these numbers. We're going to use these molar quantities as the ratios for our subscripts in this chemical formula. I'm actually going to do hydrogen next. Now, we know that these numbers, the subscripts in a empirical formula or molecular formula need to be integer values. And right here, they're not. The ratios are correct, but we need to make them integers. We need to figure out what those are. And so how you do that is you divide, as long as you can multiply or divide these numbers, as long as you do it by the same number, you're not going to alter the ratio. So we're going to divide everything here by the smallest value, which will make this 1, and then we'll go on from there. So we have the correct ratio. Now we just got to do some algebraic ironing out to get these numbers into integers. So if we go 6.302 divided by 0.9694, this comes out to be 6.50092. I'm just going to go 6.5. Let's see what hydrogen comes out to be. 8.73 divided by 0.9694 comes out to be 9, right? It's 9.00557. We're going to call it 9, again, because we know that we're going to land on integers. And then oxygen is 1. All right, now this algebraic move, helped us out a ton, right? You can see that we now have a simple integer for the subscript for oxygen and hydrogen. The problem here is carbon is still not an integer, all right? Carbon is still not an integer, and so I need to clear the board and, because I need room to work, we still have a little more work to do. So I'm just going to rewrite this. Carbon has a subscript of 6.5. Hydrogen has a subscript of, I've already forgotten, 9. And oxygen has a subscript of 1. All right, now, when you have a decimal for your subscript, after you've done that kind of first thing by dividing everything by the smallest one, what you have to do is you have to convert this decimal to an improper fraction, all right? So 6.5 is 6 1/2, all right? 6 1/2 as an improper fraction is 13 halves, all right? So we can rewrite this as carbon with a subscript of 13 halves, hydrogen 9, oxygen 1. Oh, okay. Gotcha. Yeah. Because that's the thing is once you make it an improper fraction, as long as we multiply all these numbers by the same thing, we're not going to change the ratio, and this will get rid of our denominator here. So our final empirical formula will be C13H18O2. Actually, I'm totally down to do the next part of the problem, to find the molecular formula. I just want to check to make sure that that's something you want to see. Okay, awesome. Okay, let's see. So an element has two natural... Okay, here, let me... We're going to do... okay, so let's see. An element has two naturally occurring isotopes. It has an atomic... Okay, mass. Let me go ahead and write this down. All right. So we have an element with two naturally occurring isotopes. So we've got an element with two isotopes. The atomic mass, we're told, is 45.33 AMU. We're told that the major isotope has a mass, or here, we're told the major isotope has a 65.30% abundance. Also that it has an atomic mass of 44.59. And then we're asked to find the minor isotope minor isotopes atomic mass. All right. So solving this problem actually hinges on the calculation for the atomic mass of a substance. All right, it hinges on the calculation for the atomic mass. Because if you look at it, the way we calculate an atomic mass, so if we have two isotopes, the atomic mass is a weighted percent of each. So it's equal to the isotope the isotope mass, I should say isotope 1, isotope 1's mass times its percent abundance plus isotope 2's mass times its percent abundance. All right, that is the atomic mass, and when you, or the equation for atomic mass. Now, when you look at this, in this problem, we're given the atomic mass of the element. We're given the mass of isotope 1. We're also given the percent abundance for isotope 1, and we're asked to find what is the mass of the second isotope. Now, what's missing from this equation, and Joshua, as you pointed out, the one thing that we don't have is we need the percent abundance for our second isotope if we can solve this equation, right? Because right now we have two unknowns in one equation. We either need a second equation or we need to figure out what that percent abundance is. And here's where you can get the percent abundance of your second isotope. You can only have 100% of anything, right? So the percent abundance of our first isotope plus the percent abundance of the second isotope is equal to 100%, correct? Because we're told in this problem that there are only two isotopes. We know this one. 100 is 100. So we can solve for the percent abundance of our second isotope. If we subtract the percent abundance of the first isotope, which is 65.30 from 100. Oops. So the percent abundance of our second isotope comes out to be 34.7. Now that we have the percent abundance of our second isotope, we can calculate the mass of our second isotope. All right, so we have some algebra to do. So our atomic mass (45.33 AMU) is equal to the mass of the major isotope, 44.59 times its percent abundance. You got to make sure you do this as a decimal, so 0.6530 plus, oops, sorry, I forgot my units. It's AMU times 0.6530 plus our unknown, the mass of our second isotope, times its percent abundance, which is 0.3470. All right, so first order of business is we need to multiply 44.59 times 0.6530. And the value that I get is 29.11727 units are AMU. Now we still have to watch our sig figs here, and you'll notice that both of the numbers we multiplied have 4 sig figs, so this value can only have 4 sig figs. I'm going to wait to round to the end of the problem, but I'm putting these lines here to remind myself that there's only 4 sig figs in play. And then we have plus the mass of our second isotope times its percent abundance, 34, or 0.3470. All right, next, we need to isolate the mass of our second isotope. We need to get it all by itself. So we need to subtract 29.11727 AMU from both sides of this equation. Oops. And again, let's remember that we only have 4 sig figs in this number. So we subtract this from both sides of our equation. We have 45.33 minus 29.11727. My calculator tells me that my answer is 16.21273. One of the things you'll notice, units or AMU, one of the things you'll notice about this subtraction is both of these numbers have their last significant digit in the second decimal place, so my answer must have its last significant digit in the second decimal place. So this number still has 4 sig figs. And this equals the mass of our second isotope times 0.3470. Now, to solve for the mass of our second isotope, we need to divide both sides by 0.3470. All right, once we do it, you'll notice that cancels from this side. So we simply get our mass of our second isotope, 16.21273 divided by 0.3470 gives us a mass of, hang on, I feel like I messed something up somewhere. Let me double check my math. $44.59 times 0.6530. Hang on. Hang on 1 second. Let's see, 44.59. Okay, that's what I'm coming up with as well. But something doesn't make sense. Because, yeah, like the number that I'm getting is 46.72. That's after you round to 3 sig figs. Does this work in retrospect? 46.72 times 0.3470. Yeah, no, that checks out. So that's the mass of your second isotope. Okay. Dude, you are so welcome. Oh, okay, okay. Okay. You know, 1 second. I'm gonna go release the hound. There we go. The dog has been freed, and I am back. Huh. Okay, let's try a let's try a different method. Let's see. I've got to grab my unique Discord thing. Grab that real quick. There we go. See if you can like find me as a as like a friend and adding me on Discord. That's my handle, and then maybe I'll be able to like invite you to the server. Through like a personal It sounds like the problem isn't with the invite link, but it sounds like the problem is with your account. I would try maybe making a new account. Because if you can't even log in, then that seems to be a deeper problem. So that's at least what I would recommend. Alrighty, and I actually have to run because I have to get to another class that I'm teaching. This one's on Zoom, so I gotta bounce. Victoria, maybe try doing a new account and then hitting that invite link I sent you earlier, because it's live. The invite link should work, but it sounds like you're having account trouble. So, anyways, keep in touch with email. Hopefully, we can work you into our Discord server finally. Thanks to everybody who dropped by, asked questions. It was a good office hours, and I will catch